So hello, this is going to be another technical presentation, but this is a subject I really like, and I hope you will like it too. Today I will introduce you how you can do bootstrapping for approximate homomorphic encryption. I will first start with some ring LWE basics, and thanks to Yuriko, you already have some basis with LWE. Then I will give a small introduction to what is approximate homomorphic encryption, and finally we can dive into the main topic, which is how you bootstrap approximate homomorphic encryption. So briefly, homomorphic encryption enables you to evaluate a function on some encrypted message, and here you have a diagram that splits two domains, a plain text domain and a ciphertext domain. And if you evaluate the function on the encrypted message and the decrypt, you should get the same result as if you evaluate it in the plain text. So all SIMD HE schemes, so SCMD, these are schemes that allows you to do operation on vectors values in a CMD fashion, are built on the ring LWE problems. So this is the same as the LWE problem, except it's structures and you can work with polynomials. And basically the hard problem is that given this distribution, which is a random public polynomial, some secret polynomials, and some error, it's hard to distinguish it from a fully random distribution in this ring. It's the same as the LWE problem, except it's defined on negacyclic polynomials. And how do you parameterize this scheme? So you have the degree of the polynomials, this range in the thousands, the modulus, which range into 27 bits to a few thousand bits, the distribution of the secrets, as we have seen, usually it's a ternary distribution with values between -1, 0, and 1, and the error, which is also usually a discrete Gaussian. And ciphertext are, as in the LWE, the mask, which is a random polynomial times the secret key plus the message and some error. And the decryption, again, is just multiplying with the secret key, and you can get back the message and the error. And as we have seen before, if you have enough redundancy in the message, like by example using a scaling factor, you can remove this error and isolate the message and get it back. So what operation can you do on such an object? You can do addition, which acts like adding polynomials together, polynomial multiplication, which acts like polynomial multiplication in the plaintext space, and finally, you can also do automorphisms, which acts like permitting the coefficient of the polynomial and doing a sign change on the coefficient at most. And all the functions that you will ever evaluate under encryption have to be composed with these three operations, which are the operations that are well defined in the ring. So now we can see what is approximate homomorphic encryption. So these are all the names that have been given to this scheme, homomorphic encryption for approximate arithmetic, RIAN, or CKS, but they all refer to the same scheme. So first, I need to give a small introduction to fixed point arithmetic, because this is how values are encoded. So fixed point arithmetic, you want to encrypt a fractional number or real number on an integer, and how do you do it? You simply scale it by some scaling factor, and you round to discretize it to an integer. Addition works well. You just add them together and you get the addition together. You just have to make sure that the scaling factor of the two values match, else you have to match them together. And when you multiply, you get also the multiplication of the two numbers, except your scaling factor now is larger because you have a new scaling factor that is the multiplication of the two scaling factors. We will come back to this later because this is an important part of the scheme. Now, a question is, how do you encode vectors of complex values on the ring such that you can get some nice arithmetic and not polynomial arithmetic, which is not very friendly? So the first thing that you do is you do an inverse discrete Fourier transform, and thanks to the convolution properties, this enables you to, through polynomial multiplication, get pointwise multiplication in the plaintext domain. But you are still in the complex domain. So then you have a map that maps this to the ring, but with real values. And finally, you use fixed point arithmetic to discretize it into the ring, which is modulo, where the coefficients are modulo some number. It doesn't have to be a prime, but it's, yeah. And this encoding enables you to have fixed point arithmetic over vectors of complex number in the encrypted domain. So this scheme, what can you do with it under encryption? You can do addition, And adding two ciphertexts will result in the SCMD addition over the complex domain of the vector. Same for the multiplication. It's pointwise multiplication between the values. And finally, thanks to the nice properties of the encoding, when you do an homomorphism, it acts like a cyclic shift in the vector. So you can rotate values under encryption. And this three operation can let you do pretty much what you want as long as you can represent it as a linear transformation or a polynomial multiplication. And these are, for example, the basic building blocks of evaluating a machine learning model. So you have layers of linear that are linear and layers that are non-linear. And as long as you can approximate your nonlinear operation with a polynomial, then you are good to go. Finally, now we go into the main topic, which is bootstrapping. So a scheme is said to be leveled if, for any function f, there exists a set of cryptographic parameters that enables you to evaluate this function and decrypt it to the correct decryption. So in theory, you can evaluate any function if you choose a large enough parameters. But in practice, the size of parameters, they grow really fast with the depth of the circuit, and you will easily reach parameters that are impractical. And the bootstrapping is the ability for a scheme to evaluate its own decryption circuit under encryption using an encryption of its secret key. And what this enables is that you can decorrelate the complexity of the circuit from the parameters, and this enables you to evaluate arbitrary depth function for a fixed set of parameters. So now we get back to our encryption, and this looks similarly to what we saw before, except this is called Approximate Homomorphic Encryption because you do not distinguish between the error and the message. They are mixed together and you deal with it. So you store the message in the lower bits along with the error. Now when you multiply under encryption, what you get is a new message that is larger because you have a scaling factor, and you need to manage this scaling factor, else it can grow exponentially. And how do you do that? You truncate the lower bits. But as you can see, your modulus Q, so this is just one coefficient, but you have thousands of them, it gets reduced by this, new scaling factor. So the ciphertext is smaller. At some point, you cannot do a new multiplication because else your message will overflow and get destroyed by the modular reduction. So practical and efficient parameters can allow you to evaluate circuits that are about 30 rescaling, so 30 chain multiplication. But what if you want to evaluate a larger circuit, like 300 depth or 1,000 depth? At some point, you will get, you cannot use practical parameter service. And so the solution is to decrypt and then you encrypt. But what if there is a way to, from a ciphertext with a small modulus, get back to a ciphertext with a largest modulus without having to decrypt? And this is what bootstrapping is for this scheme. It's the ability for this scheme to have a circuit that, given a ciphertext that cannot do any operation, outputs a new ciphertext that can do at least one new operation. And if you can do that, then you can evaluate whatever you want. So how do we do that? So the first step, obviously, is to say, OK, I have this small ciphertext at the small modulus Q, and I will say arbitrarily, now it's not at this modulus Q, it's at this new big modulus Q. What this does is that it acts as an implicit decryption done modulo Q. The issue is that the decryption is done modulo big Q and not small q, and thus you don't have the modular reduction you would have if you were doing it modulo small q. So you get a new ciphertext, except that it will decrypt to what you want, your message, plus an unwanted polynomial that is scaled by this small modulo q. So what can you do? Well, obviously you say, okay, I want to homomorphically remove this small polynomial and do a modular reduction modulo q, but under encryption. Another issue is that this small polynomial is not encoded. It means that it does not follow this SCMD arithmetic that we introduced before. It means that it will, if you do a multiplication, it will not multiply pointwise, it will do a polynomial multiplication. So again, the solution is to say, okay, I will homomorphically encode this polynomial. And to do that, I need to apply homomorphically the inverse discrete Fourier transform. So what are the steps of bootstrapping? First, you have this implicit decryption where you just reinterpret your ciphertext from your small modulus to your large modulus. Then you apply under encryption the encoding, which is an inverse discrete Fourier transform. Then you have to find a way to do the homomorphic modular reduction under encryption. And finally, you do again the decoding to get back your message, but without this polynomial that you do not want. And now we'll go into more detail for each steps. So the forward and backward discrete Fourier transform are simply linear transformation, and as we saw before, you can evaluate them with addition, multiplication, and vector. It can be expressed as a matrix vector product, and you can express this matrix vector product with plaintext multiplication and rotations. So this operation is fairly easy to do under encryption. It's simply rotation and plaintext multiplication. It's quite fast, and it has been. For the last 3 years, there has not been really an improvement on how to do it. However, the homomorphic modular reduction is harder to do because the issue is that it's not a linear operation, and it's not an operation that is easy to represent with a polynomial. So the first proposal for how to do this bootstrapping was to use trigonometric functions because they are periodic and they are smooth, which means that you can have a nice polynomial approximations. So here it's the graphical representation of a scale sign function, and we can see that when your value is close to an integer, then it nicely matches the function that is x mod 1. The only issue is that you need your fractional part, so your message, to be really small compared to what you want to remove, else you have an approximation error. So another proposal that was made later was to compose it with the inverse in a function, and now you get something that looks really nice. So to be all of this is done with polynomial, and you can approximate this function with polynomial really nicely and compose them together. So you can do that, but the only issue is that now the circuit is more complicated and it's not always worth it. In fact, how to do this homomorphic modular reduction has been a subject of research for the last years, and you have many papers that have proposed a different approach. But in the end, they all have their drawbacks, their pros and cons, and nothing really stands off. And for a long time, the question was, how can we get something that is really precise and that does not need like very large parameters and is unpractical? So yeah, just the references if you need them. And recently, there was a work that was kind of the breakthrough that showed how you can get arbitrary precision bootstrapping, because the issue of the bootstrapping is that you have a fixed precision that is really hard to get above without having to increase the parameters to something that becomes impractical. And they show how using a simple black box bootstrapping, you can construct a new bootstrapping circuit that has a precision that is twice as the previous one, and how to compose them to have an arbitrary precision bootstrapping. So the main idea is that you bootstrap the error that is added by the previous circuit. So an example here is you have a plain text message that is scaled by a scaling factor squared, with a bootstrapping that has a precision that is approximatively the same as the scaling factor. So you do a first bootstrapping, you get your message back, plus the error times the scaling factor, because this is the error that the bootstrapping would produce. You take it back, you subtract from the original message. This gives you only the error of the previous bootstrapping. You bootstrap this again, you get your error that is bootstrapped at the maximum modulus, plus some small error. And then you subtract again, and you get your original message, but you have replaced the previous error by something that is smaller. And you can continue as much as you want until you reach the minimum precision that the scheme provides. Another thing I did not talk about is that this bootstrapping is not ensure that you always end up with what you want. The issue is that when you do a polynomial approximation, you define it in some interval. And this interval, you have to make sure that your polynomial that you want to remove, the coefficients, are within this interval. And the size of this polynomial is defined by the density of the secret key that is used by the scheme. So you kind of have to have a probabilistic bound to say, okay, it's very high probability that this coefficient will fall into this range. Because if you want to cover all the possible range, the polynomial to the approximation is very large and it's impractical. And until a few years ago, it was not really talked about, but the failure probability was quite high, actually. If you have a lot of number of slots, it could be like 1 in 60,000, which is not acceptable. And so how to reduce this failure probability? Then just use a smaller secret. The issue is that if you use a smaller secret, then to stay secure, you have to use smaller parameters. And it was not possible to achieve a bootstrapping that is at the same time 128-bit secure, has a negligible failure probability, and is practical. And the solution is to leverage the property of the ring LWE, or the LWE, which is that the smaller your modulus is, the more secure it is, and the sparser your secret can be. So the idea is that since what you give as bootstrapping has a very small modulus, then it's much more secure than the larger instance, but you still have the same ring degree. So you can use a very sparse secret with this small modulus. And the idea is to encrypt this very sparse secret at this small modulus, homomorphically switch to this new secret, you raise your modulus back to the big modulus, and then you switch back homomorphically to the original secret key. So what this enables is to decorrelate the complexity of the bootstrapping from the secret key that is used for the rest of the circuit. And with that, because you are able to use a much sparser secret that you would be able to if you use the original secret, you can have a nice polynomial approximation which have an interval that is large enough so that you can prove that the failure probability is as small as the security parameter. So now some concrete numbers. Everybody says that FHE is really slow, but actually the bootstrapping for the CK scheme is has the largest throughput, and it's measured in microseconds per slot. So it takes approximately 10 seconds on a single core to bootstrap values have a precision of 27 bits, which is more than float 32. Be able to do 10 sequential multiplication after that, and with an amortized time per value that is in the order of 300 to 150 microseconds. And the plain text space is quite large, as you can see, 2 to the 15 or 2 to the 16 values that are bootstrapped in parallel. So all of this is implemented in Latigo, which is a Go module that implements full RNS ring WE-based homomorphic encryption and multi-party homomorphic encryption. And Latigo is currently the library that provides the most usable, complete, advanced, and customizable bootstrapping for approximate homomorphic encryption. Thank you.
Thanks for questions.
Ask why bootstrapping has fixed precision rather than, or fixed precision out of the box, where just in general.
You mean refer to the slide with the numbers?
Yeah.
So you can parameterize how you do the polynomial approximation, what is the level that you allocate to it, because the bootstrapping it's a circuit, so everything it consumes, it's something less you can use afterward. And so it's a trade-off. Do I want a very precise bootstrapping, but I have to do more of them, or can I afford to have something that is okay, but I can do less bootstrapping? And these parameters, it's out of the box nice trade-off between speed, complexity, what you can do after it, and precision. But if you want, you can have more, you can have less, but you still have to be quite an expert to know how to parameterize it properly. This is why we have out-of-the-box parameters.
Gotcha. Thank you.
Any more questions? What is like a real example about the time cost of successful bootstrapping?
Time cost, what do you mean? Like how much time it costs to do a successful bootstrapping?
Yes.
So in the slide, it was about 10 seconds.
Okay.
But you can do it faster if you need less, slower, and this is on a single core and with no parallelization. But I'm aware that if you have a nice implementation with GPU, it's like 200 milliseconds.